Welcome to my YouTube channel. So in the today's video, we are going to learn how to generate an amplitude modulated signal on MultiSim. So let's begin this discussion. So there are several methods by which we can generate an amplitude modulated signal on particular the multisim or any breadboard. Okay, but today the generation of the amplitude modulated signal, I will be using one of the method which is called as the square law modulator method. Okay, so using square law modulator, this is the basic block diagram in which you can see in this block diagram. First of all, we have to take the message signal empty, and this message signal has to be added with the carrier signal. Okay, first we need to add these two signals together. Okay, generally we are choosing the carrier signal to be a sinusoidal signal, okay, of high frequency. So these two signals must be added together, and after that this signal must be passed through a non-linear device. Okay, so after passing through the non-linear device, we have to design a band pass filter of a particular pass band frequency. Uh, and then when we pass this output of a non-linear device, then the resultant signal will be our AM signal. So in theory, you can find these expressions. Okay, so if you go through the theory of amplitude modulated signal generation using square law modulator, you will find the mathematical expressions, and ultimately you find that this V output signal will be taking this form. Okay, it will be taking this form. So V output will be equals to something AC 1 plus 2B upon A MT cos 2 pi FCT. Okay, so here I'm not going to tell you about how this expression comes. Okay, when I will be discussing in the theory, you will find another video lecture. Okay, I will be uploading soon. So in that lecture you will find that how this expression comes. Okay, but today we are just going to see the laboratory part. Okay, how to generate the amplitude modulated signal. Fine. So this will be your expression. So ultimately this expression can be rewritten as V output equals to AC dash 1 plus KAAM cos 2 pi FMT cos 2 pi FCT. Considering that our MT is a sinusoidal signal, means MT is nothing but your message signal. So message signal can be anything, but here just for the simplification, we are taking MT equals to AM cos 2 pi FMT. Okay, you remember that here the message signal frequency should be much lesser than the carrier frequency. Okay, and then we can define a term which is called as the modulation index, that will be equals to Ka multiplied with the Am. So we can further calculate the mu. Okay, so you can see that basically we need to obtain this type of signal. Okay, this particular waveform is the time domain waveform of our amplitude modulated signal. Okay, so we actually we have to obtain this particular signal. So here what we can see is this is our carrier signal, and the this carrier signal's envelope is actually carried by the message signal. Okay, so basically if you see the envelope of this carrier signal is nothing but your message signal. Okay, so this way we are actually modulating the carrier such a way that its amplitude will be directly proportional to the amplitude of the message signal. So here you can see this is our message signal. Okay, so its envelope becomes the message signal. That is more important to understand. So basically this particular signal we need to obtain. Okay, we want to obtain this particular signal, which is our amplitude modulated signal, or also it is called as the conventional AM signal. Okay, another name for the same thing is double sideband large carrier scheme. Okay, so it is double sideband large carrier signal. So what we can do is we have to, first of all, we have to implement these block diagrams. So that block diagram you have to keep in mind. So first we have to implement one of the adder. Okay, that adder should be able to add the two signals. Okay, message signal and carrier signal. And after that, this output of the adder should be passing through a non-linear device. Okay, so we can choose a diode. Okay, diode is also a non-linear device. Fine. So we have to pass this output of the adder. Okay, that I will be implementing by using the op-amp. Okay, it is very simple to implement an adder circuit by using the op-amp, so that we can implement, and then the output of the op-amp will be passing through the non-linear device, that will be our diode. After passing through the signal through the diode, then we have to construct the band pass filter. Okay, and then through after passing through the band pass filter, you remember that the band pass filter characteristic should be like that, so that the output of the band pass filter should be a AM signal. Okay, it means that there must be a certain pass band in which the output, when it will be passed through the band pass filter, the output will be a filtered signal, and that filtered signal your AM signal. Okay, so you remember that at this point the output will not be a AM signal. It will consist of large number of harmonics and other parts, other frequency components will also be present. Okay, but once it will be passed through the band pass filter, all other unwanted frequency term will be removed or filtered out, and only the desired frequency component will be passed through the band pass filter, and that signal will become your EM signal. So that we have to remember. Okay, so let's see how to implement this circuit. As I told you that the summer can be made can be easily implemented by using the our op-amp, and nonlinear device is nothing but our simply a diode, and then the band pass filter I have already implemented in my previous YouTube lectures, so that you can refer. Okay, I will also share the link in the description box, so that you can refer if you have not seen that particular video, how to design the band pass filter. So after having this one, now we can look at how this circuit can be implemented. Okay, so this is our circuit onto the multisim. Here you can see that this is the first part. This is our adder part. Okay, here you can see we are having this adder part. So I have used the 741 op-amp, and then I have implemented one adder circuit. Okay, so this is our adder circuit. Okay, so here I have just resistance of 1.5 kilo ohm, 1.5 kilo ohm, another resistance of 1.5 kilo ohms. Okay, you can choose all equal values. Okay, and then here I have connected, from this point I have connected the masses signal, and from this point I have connected our carrier signal. Okay, as you can see in this particular block diagram, we have to add this two signal. Okay, masses signal and the carrier signal. So this is what I have done here. So here you can see here the carrier signal I have connected over here, and this is our masses signal. Fine. So after having this adder, the output of the adder is at this point, at this terminal, terminal number 6 of the op-amp. Okay, we obviously give the power supply to the op-amp for its proper functioning. Okay, and then we have the output at this particular terminal, and that has to be passed through a non-linear device. So here I am using one BH62 model number of our diode. So I have to use one diode. Okay, so this diode I am using as a non-linear device. Okay, and after having this non-linear device, I said we have to use one band pass filter. Okay, so I have already implemented this band pass filter in my previous video lecture. Okay, whose carrier frequency, as I said, there must be a certain central frequency, and there must be a certain bandwidth of that particular filter. Okay, so that I have already implemented in my last video lecture. Please refer to that one. So I am just, for your sake of understanding, okay, you can just go back to this particular thing I have already explained in the last lecture. Okay, so here you can see that this particular second order band pass filter I have already implemented, and we got this particular it's a frequency response, okay, of second order band pass filter. So if you remember, we actually implemented this filter, and we got the central frequency as equals to 9.1 kilohertz. Okay, we got 9.1 kilohertz, and the 3 dB bandwidth of this filter that we got is around 800 to 900 hertz. Okay, so that was our 3 dB bandwidth. So basically, once we understood the characteristics of the band pass filter, okay, what we can choose is we can choose the carrier frequency for amplitude modulation accordingly. Okay, so what I have done is, because I know that the central frequency of this band pass filter, okay, of this particular band pass filter is 9.1 kilohertz. So what I'm doing over here is I'm just making the carrier frequency is equals to 9.1 kilohertz. You just see this, okay? I'm just making this carrier frequency I have taken as a sinusoidal wave, and I have made this frequency equals to 9.1 kilohertz because this is the central frequency of this particular filter, okay? Remember that if you want to change the carrier frequency, okay, if you want to make it 10 kilohertz or 20 kilohertz or some other value, obviously you have to design your filter accordingly. That you have to remember whatever the equations that I have told. So that equations you have to follow, and you have to change the center frequency of this particular filter first, and accordingly you have to choose the carrier frequency. Otherwise, if you choose the carrier frequency something else, let us say if you are choosing 20 kilohertz, if you don't change the parameter of the filter, you won't be getting the output properly. So that you have to remember, you have to keep in mind. So I will be using this carrier frequency equals to 9.1 kilohertz, and this you can say it is the V maximum, or its peak amplitude of the carrier, which is generally in the equations written as AC. So that AC I will be taking as 1 volt. Okay, it will be kept constant. Okay. Now we have to choose the our masses signal. Okay, so this is our masses signal. So here you can see, as I said, the our masses signal should be anything. Okay, it can be sinusoidal signal, it can be square wave, it can be triangular wave, it can anything else. Okay, but just for the simplification, we have taken the sinusoidal wave. And you remember that when we are modulating the signal, okay, when we are doing the AM modulation of any masses signal, okay, then after doing the modulation, generally if the masses signal frequency is FM, okay, maximum frequency is FM, then its bandwidth in the AM modulated signal will be becoming 2 FM. That we have to remember, okay. And I said that the frequency means the central frequency of this particular band pass filter is equals to 9.1 kilohertz, and its 3 dB bandwidth is around 800 to 900 hertz. Okay, so we cannot make the FM too large. Okay, I have just taken 200 hertz. So the maximum AM bandwidth that we are going to get is equals to 400 hertz. So basically this filter will be sufficiently large, means its 3 dB bandwidth is sufficiently large to handle this signal. Okay, that you remember. Okay, so that's why I have chosen equals 200 hertz. If you want to make it 500 hertz or 600 hertz, you have to increase the 3 dB bandwidth of this particular filter. Otherwise, again, you won't be able to get the AM modulated signal. That you have to remember. That is a very important point over here. So you have to just choose this 200 hertz. Then I have taken the amplitude equals to 0.5. Okay, this is our AM. Okay, the maximum amplitude of our AM signal means our masses signal. Okay, so that is where 0.5. And now we can execute this circuit. Okay, so after execution, we are supposed to get the AM signal. Okay, so now once we execute this one, okay, you can just double click onto this. So you can see here, we are going to get this particular AM signal. Okay, a very beautiful AM signal you can observe from this particular oscilloscope. So this is our AM signal, okay, that we are getting. You can also compare the same graph from this particular picture. Okay, so in this particular waveform, you might be finding in many of the books that the AM signal will be look like this. Okay, so the carrier, the whatever the carrier that we have, so its amplitude is actually will vary according to the masses signal. Okay, so this is what we are getting over here. Okay, here you can just verify it. Okay, this is our masses signal, and this is our carrier signal of very high frequency. You can obviously measure the frequency of this carrier. Okay, and even you can see this the frequency of the masses signal also. Okay, that you can measure. There is no issue. You can just stop it. Okay, and then you can just see this is the top, and here again it is the top. Okay, almost how many divisions it is covering, you can just see it is 1 2 3 4 and 5 divisions are covering. So it is 5 divisions means it is total 5 milliseconds. Okay, so obviously it is 200 hertz signal. Fine, so that way you can calculate. It is very easy to calculate and verify these signals, means these things I have already explained in my previous video lecture, so please refer it. Okay, So this way, now I will be telling you one important parameter again. Okay, so in the amplitude modulation, you just see in this particular case, we are taking the carrier frequency equals to 9.1 kilohertz and the massive signal frequency equals to 200 hertz. Okay, so here you can see that I have taken the AC equals to 1 volt. Okay, that will be a constant value. And then we have to measure these things. Okay, V maximum, V minimum, and then we have to calculate the modulation index. Okay, so AM is equals to zero point 0.5 volt and AM equals to AM equals to for 1 volt. We can do this calculation. Okay, and then we can measure what is the modulation index. So please just recall this equation. Our modulation index mu is defined as V max minus V min divided by V max plus V min. Okay, so what is V max and what is V min? So in this amplitude modulated signal in the time waveform, in the time domain waveform, if you see this top value, okay, this top value here, you can see this is the top value is your V maximum, and this bottom value, okay, this amplitude is referred as V minimum. Okay, that you remember. So by calculating these two things, we will be able to calculate the modulation index mu. That will be equals to V max minus V min divided by V max plus V min. So modulation index is one of the very important parameter in the case of amplitude modulation. Okay, so that we can calculate, and that calculate, and then we can calculate the what is the modulation index we are getting. So for example, in this case, if we want to calculate the V maximum and V minimum, just you expand the signal a little bit. Okay, so I'm just expanding this signal. Okay, so you can expand this signal a little bit, and then you can see here we have to calculate the V maximum. So just to go to the top, okay, just go to the top. Here you can get this value equals to, here you can see the this pointer is nothing but your second pointer. Okay, messaging pointer is 2, so this T2 here you can see it is 5.871, or it may be more. Okay, you can just cross check it again. You have to take the maximum value, so 5.834 or something. Okay, so I have measured it, it is coming as 5.865. Okay, so you can just measure it uh, carefully, so you will be getting this maximum value. Okay, so that value you can calculate and then you can note it down. So for example, you can just bring this pointer. Okay, this 5.888. Okay, so if you do this measurement properly, you will be getting the maximum value 5.888. I got, so okay, 5.888. So that you can write over here. I had written previously 5.865. You can make it 5.888. Similarly, you can just measure the V minimum value. Okay, you can go back and you can measure the minimum value. Just you try to move this curve. Okay, move this waveform. Here you can calculate the V minimum value. Okay, so I think this may be the minimum value, or this may be, so either this or that. Okay, so approximately this value you are getting as here you can see it is 1.796. It is 1.796. So I have written it is as 1.792. So I think it is in 0.796. Okay, so once you will do this, the mu is automatically calculated based on that particular formula. We are getting 53.25. 3516 modulation index. So this is our modulation percentage. Okay, 53.25. You remember that it is modulation percentage because the absolute value of mu cannot be greater than 1. Okay, so maximum modulation depth will be 100%. Okay, if you are calculating in the percentage form, otherwise it will be less than 1. Okay, it cannot be greater than 1. Okay, so it is either 0.53 you can say, or it is in the percentage form it is 53.25. Similarly, you can make the EM equals to 1 volt. Okay, just go back again, and then you can just make this amplitude equals to 1 volt. Okay, once you will make it 1 volt, and then if you see this waveform, okay, here you can see this waveform. Okay, so here you can observe this waveform. This is amplitude modulated signal, a very beautiful signal that you can get. Fine. So this is our amplitude modulated signal. Again, you can do the same measurement. Okay, I have already done it for you. So you can just do this measurement, V maximum, V minimum. You will be getting that the modulation depth is now increased. It has increased to 89.48%. Okay, so it is 89.486. So this way you can conduct your experiment just for your understanding. I will be showing you that if we change the carrier frequency, okay, if you change the carrier frequency, let us say if you want to make it 20 kilohertz, okay, let's see what kind of output you are getting. Okay, just to try to see this one. Okay, the output is not properly coming out. Okay, it is not properly coming out. You just see it is not coming properly. Okay, because the central frequency is different. Okay, it is not coming properly because the signal is actually getting attenuated a lot. Okay, the attenuation is too much, so still some part you are getting because obviously it is a filter, but you can see this amplitude is very small. The signal got attenuated a lot. Okay, so that attenuation is too much. Fine, so that we have to take care, because even if you make it 40 kilohertz, then again the signal will be getting attenuated a lot. Okay, just try to see this picture again. See, in some noisy kind of signal you are getting, and this signal is actually looks like EM signal, but the amplitude is very much small. Okay, very small amplitude is coming over there. Okay, similarly, even if you can make it, let us say I just bring back to 9.1 kilohertz, and if you try to increase the frequency here. Okay, if you increase the frequency like 1 kilohertz, let's say, if you want to make it 1 kilohertz, again some kind of problem you may observe in the waveform. Okay, some kind of problems in the waveform you may observe. Okay, it will not be exactly the same waveform that you are expecting. Okay, so because the bandwidth will increase. Okay, because bandwidth of the signal will increase, and the exact waveform you will not be found. Okay, so that you have to take care. Okay, while conducting this experiment. Okay, I will be discussing the demodulation part. Okay, demodulation part in our next video lecture. So I hope this discussion must be okay. Even you can change the frequencies. You will find that there is a kind of means signal that will come out that not corresponds to your AM signal. So I hope this discussion must be helpful for doing this experiment. So please try to implement this AM modulation. I will be coming up with the next video lecture in which I will be using the same circuit, and I will be implementing the receiver part, means the demodulation part of the AM signal. Okay, so I will be doing this demodulation by using the envelope detector, which is a very simple detector. Okay, so that detector I will be discussing in our next video lecture. So I hope this must be clear. If you have any query, please drop your queries in the comment box. So thank you for watching. Okay.